Hello and welcome to the channel. This week we're looking at one of my projects. This is something I've been developing. This is, well, I've called it a VFO or DDS VFO, but it's much more than that. It's specifically designed for modifying radio equipment. So it means that if we've got a piece of old radio equipment, this can take over the role as the local oscillator or local oscillators, because there's 2 outputs and possibly 3 should you need it. But it means you can actually control the radio via the local oscillators, and it does a lot more. So there's a lot of I/O and communication and all kinds of stuff going on here. I was initially asked by people from the 11 meter community, could I develop a board or make kits following one of my projects where I modified an old 11 meter radio. Now that was incredibly complicated and it's not something I could very easily replicate. So everything that I've learned from that, I've actually developed this board, and I've reached out to the ham radio community and the 11 meter community, specifically people who modify and customize radios, and found out, try to understand what the problems that they face, because there are people making these things. They're basically cobbling sort of these evaluation boards and Arduinos and stuff together. But there's issues, and hopefully within this I've managed to iron a lot of that out. So what I'm going to do, we'll go through the features of this, what it can actually do. We'll go through some of the theory of operation, so we can have a look at the circuit diagram and put it on some test equipment, and then we'll take a look at see if we can possibly modify a radio using this unit. Okay, so if you're new to the channel and you like this content, please consider subscribing or hitting the like button, as it really helps the channel. We're trying to grow the channel, so thank you in advance for your support. Okay, so at the heart of this we've got this microcontroller. This is from Renesas. It's the RA4M1 series microcontroller. It's got an ARM Cortex M4 processor in there, and the clock speed's 48 megahertz. This is a 32-bit device, and it's very capable. I've been playing with it, and I must admit I am impressed with how well it performs. Now this thing's got 32K of SRAM. We've got 256K of flash memory. It's also got a 12-bit DAC, digital to analog converter, so it can quite easily produce tones, which I've been playing with. At the moment, it will quite happily produce CT/CSS very accurately, I may say. But it'll also do DCS, which I'm also playing with, and FSK, and possibly FFSK. In fact, I'm pretty certain I can get this to do what most of the tone generators that you buy, for sending digital. I'm pretty sure I can actually write the code to do that. But, again, it's just time, it's development work, and I'll get there when I get there. It's also got 14-bit A to D pins on there, so on the analog pins, so 14 bits gives us a really high resolution. So yeah, it's quite capable, and I found for this it's just the job. Now, a good thing about this is that it will actually support USB directly. I don't need a UART, so you can actually connect up the USB here. You can connect it to a computer, and as I say, this has got an Arduino bootloader on there, so it means with the Arduino IDE you can program this thing. Now I'm going to make the code for this open source, and you can use it, modify it, or write your own code, but it just makes it ease of use, and it's nice and standardized from those nice people, those nice Arduino people. And I like Arduino because there's lots of libraries. There's a lot of people doing a lot of development work, a lot of hard work gone into it. It's open source. And I thought, well, if I put it on there, I mean, it's just going to be a bonus. And it just makes it nice and easy. You can, of course, load in different bootloaders. You can put the Renesas bootloader and use their IDE for programming. It works somewhat different. You don't use pin mode and all that. You have to address the registers. Oh, incidentally, there's a lot of pins on here that are unused simply because the IDE, the Arduino IDE, you know, it doesn't see them. But I've just figured out a way you can actually address the registers directly, and then we can use them for whatever we want, you know, depending on, if you look, I'll go through on the data sheet, but you can, you know, a lot of them are universal. You can use them for just about anything. Now this is good for, well, I'm using the I2C section of it for communication. So we've got 3 I2C ports on here. These are 5 volt standard, and this is a 3.3 standard. Okay, so the board will produce 2 separate frequencies up to around 220 meg, 220 megahertz, and they're stable, you know, totally independent, and they're stable well within 1 hertz. So you know, 1 hertz it's quite good. Now, what's driving this is the SI5351. Now, I nearly went with an analog to digital converter, but in the end I settled on this, as the more I found out about this IC, the more I played with it, the more I liked it. And a lot of it's to do with the cost, because these are reasonably cheap. And this is the B version, so that means it's got a VCO in there. And it simply means that we can actually modulate FM, and modulating FM works quite well. That was a bugbear that a lot of people came back with. A lot of these boards that are out there, they don't modulate FM, and the problem is, because you're actually modifying radio equipment, you're taking away the synthesizer, and that's, you know, around the PLL VCO section of the radio, that is generally where the FM gets modulated. It just, you know, the audio signal pulls the VCO, and that's how they generally modulate it. So yeah, this will quite happily do that. So the audio comes in here. We've got a deviation level here. Now I'm getting up to 12 kilohertz deviation, no problem. That's by adjusting this, but there's actually, in the code, you can actually adjust it. I don't know what I can take it up to. It's something I've got to spend a bit of time with. But for general communications, something like 1.5 or 2.5 kilohertz deviation, this will adjust down, no problem. Now there's a bit of cap here, and there's a few bits in here which is putting a bit of pre-emphasis on the FM signal. So, you know, the FM, it's the audio signal we want to modulate. And I've got it, where I've got it, I've been tinkering. It works really well. It does very good voice. Now, as I said before, this thing will produce tones, and there's a little jumper here. So if you want the tones to just modulate the FM, you can just literally just have the jumper in one position. And then if you want, you bring it over to where it is now, it just means it's got X, it means external, and the tones it will generate will come out of this header here. And then you can actually plug that into the radio wherever you want it. Yeah, this is going really well. Now, another bugbear that I got told a lot, you know, never the same frequency twice. They're all over the place, these things. Well, the development boards are, because they just use in tuppence halfpenny oscillators. They use, like, it's just a cheap crystal oscillator. They're very, well, it's not an oscillator, it's just literally, it's just a crystal. And they're very temperature sensitive. So the basic what I'm using here is a TXCO. This is a temperature controlled oscillator, and it's got a stability down to plus or minus 2 parts per million. Obviously, the way these things work, that doesn't mean it's 2 parts per million across the board here, because obviously this is it does multiplication and division. so it'll accentuate the obviously what the difference is. But I'm getting 1 hertz stable, stability across the line. And, obviously there's a calibration routine. The calibration routine isn't a case of just offsetting the frequency in the software, in the code. What you have to do, there's some little registers in here, and there's a little, I think there's a little divider network for the crystal oscillator, and that will set it where you need it. So you have to go through that routine, and once that's been done, then across the spectrum it will stay in by just adjusting, just by offsetting the frequency. At a certain point you'll probably go, it'll be okay on that frequency, but as you go away from it, it'll start going off. It'll start running out. So yeah, SI5351-B, that it's working really well. And if you look here, by the way, you can see these little links. So this is a prototype board, by the way. And basically what I was doing was, I was actually, because I was running some of the outputs differentially, and I've got some little mini circuits, transformers on here with center taps. And what I was doing was just experimenting to see what would happen. I was looking for second harmonic suppression, but to be honest, the juice ain't worth the squeezing. There's a point of diminishing returns. So I've linked those out, and then the next boards won't be there. It's just a cost. It's what you get. It's just not worth the effort. So yeah, the output levels from this, by the way, yeah, I think we've got 4 settings. So we can set from 0 dBm up to approximately 10 or 12 dBm output, which is quite, is good enough to drive sort of, these diode array mixers, because they generally need quite a high LO. Yeah, that's it. So the lowest setting, it's about 0 dBm or thereabouts. Okay, so let's talk a bit about these headers. We've basically got 3 headers here. Now these are for rotary encoder inputs. Now this was one of the biggest bugbears. A lot of people have had a lot of problems with rotary encoders. They don't work properly, they skip, they pop, they jump, and they go wobbly. This people have really been struggling. I've found some solutions to that, so later on in the video we'll go through exactly what those are. But basically these headers they're 5 volts, so they'll support a rotary encoder and a switch. It supplies the power. The board supplies the power via the header. Everything I've made is all modular, so it all fits together with ribbon cables, and even the rotary encoder's got a little back board with some signal conditioning on there, and decoupling. So, and they all work really well. So these ones you can actually put just standard rotary encoders on there. Mechanical rotary encoders. You can also use optical. This one here, this one is designed specifically for high-speed rotary encoders. And again, we'll explain how that works, but this will take really high-speed rotary encoders. There's another little board that goes with this, but again, we'll show you that as we go on. Up the top here, we've got a header. Now, if you notice, that's a different form factor header to this one. Now, what these are sensing pins. So these connect up to the radio, and basically what it does, it senses what mode we're in, whether we're in AM, FM, upper, lower sideband, carrier wave, and so on. So there's 5 connections there. Now, there's another header next to it, and this one has got, it's a 12-pin header, and then there's another 10 pins. These are IOs. Now, just go back a second. Yeah, so these sense, so anything over, it doesn't have to be sort of 5 volts, anything over on these, over sort of like 4 volts to 16 volts, it'll register as it being in that mode. So they normally have a rotary encoder on them on the on radio equipment, or you may be picking it up from somewhere in the radio, but this will sense from about 4 to 16 volts, will register as being in that mode. Okay, and then we move over to this side. We've got a 12-pin header, and what we've got here is a ground and a 5 volts. Now this is a reference, a very clean low dropout 5 volts, and I'll explain why. This IC here is a multiplexer. It's a 16:1 bidirectional analog multiplexer. It'll run at 100 megahertz. Obviously we're not going anywhere near that, but this thing works really well. But it just means that I can expand the I/O capability of the microcontroller. So on these you can actually attach potentiometers. So one side of the potentiometer will be at 5 volts, the other side will be at ground, and then the wiper as you go around will give you a voltage swing. So you can use these for RIT, XRITs, you can use it for squelch, so that it can actually sense where the squelch level is. Again, we can talk a little bit more about these later. And then there's other operators. You can put switches on them, or you can assign them to do whatever you want. Now these are only 5 volts, so this is a 5 volt input here. Now if you noticed underneath, you're probably wondering what this is for. So this, what looks like an IC, this is a 10 kilo ohm array of resistors, and these this array here just switches them down to ground individually. Now the reason I want to do that is obviously we've got RF coming in, but for potentiometers we don't want the 10k pulling to ground, so you can actually switch it off. For a normal switch, it's being pulled down to ground. When you throw the switch, it'll go to 5 volts, and then it'll register for whatever you're doing, with the device. So for the case of just having a nice little switch on there, so if you're using pots, you just turn that channel off. Now, saying that, there's been a lot of thought gone into this, because I don't know if you can see a lot of these tantalum capacitors. There's a lot of decoupling on here. This is designed primarily to go into vehicles, in hostile environments where there's loads of RF flying around, and it's designed to be stable. So what I've done, I've really gone overboard with the decoupling. I've been giving the thing hell, and it certainly does the job. Now this header here, we've basically got a ground, we've got our 13.8 volts. Now this will run from anything between 8 and 16 volts, because obviously it's got onboard regulators. So there's 13.8, then there's a switch 13.8. Now there's a good reason for that. I'll come back to that in a second. And we've got a TX8. So we know whether the radio is in transmit mode. So when you keep the mic, the TX8 goes up. And again, this only needs to see anything over 4 volts, and it'll register as the radio's in transmit mode. Now, for sensing this, there's very, very good reasons. One of which is obviously different modes may have a different frequency offset on the local oscillator, and you can actually set the offsets. Now, it could be on LSB. You may want to drop or increase the local oscillator by 3 kilohertz to simply move the signal into the bandwidth of, say, a crystal filter. But some radios, they all differ. So it's completely settable in the code to do this. Now, one thing I keep going on about is code. This will be able to be set using menus on LCD screens, which we'll get to the screens as we go on. But yeah, that's another bugbear. A lot of people, oh, I don't like coding, and they run away, you know. But yeah. So getting back to here, we've got so we pick up the TX8. We're also picking up the signal strength coming in to the radio. So we just literally pick it up off the meter, off the signal strength meter. Because generally one side of the meter's to ground and the other side is the signal that's driving it from, you know, it's normally in the IF sections of the radio where it's sensing the actual level. So you can actually remove the meter, and that's what this jumper's for here. So if you remove the meter, you put this jumper in, and what this does is just literally puts a 600 ohm resistor, because most meters are 600 ohm, and puts a little damping capacitor in there. And if you want to connect directly on to keep the meter going, we take this off. So the resistor and the damping capacitor is not there, so it'll have normal operation. And what this does, this feeds through into this little op amp here, which half of it's being used by the deviation and the other half's for signal strength. We've got a pot here, that's to set the signal strength, and that information goes into the microcontroller. Now we can use that, we can use it for squelch, so we can, if we had a squelch pot connected on here, we can actually set we can make it so that, you know, we set levels. Now there's outputs that can come off from this. It's going to be on the next gen board, but that will control the squelch. That, you know, again, I'll talk a bit more about that later, because that's a lot to do with CT, CSS and DCS. So really want a method to control the squelch. Yeah, so that's the signal strength. And then we've got a couple more IOs on here, but that's basically it. You know, the unit is designed, it's on little plastic standoffs, so you could literally just get some araldite, glue this to the lid or whatever of the radio that you're going to put it into, and then obviously these all just connect up. Now everything I've designed is modular, so all the little rotary encoders and such like, and displays which you can put on there, because this will run LCD.matrix directly, OLEDs, and I'm also looking at 7-segment arrays that it'll run directly off the I2C, so you just literally plug them in, and these are all daisy chained as well, so you know, you go on one and daisy chain onto the other. It's just that they just need an individual hexadecimal address, so that the microcontroller can identify which one it's talking to or receiving information from. But that is basically it. Oh yeah, and getting just one thing, yeah, there's 2 voltage regulators on here. We've got one that's doing just the general purpose heavy lifting, that supplies the 5 volts that comes out of these that run the encoders, and also does the I2C 5 volts. And then there's another one here. Now this is a very low dropout 5 volt regulator, and it's also got an inhibit on there, which is controlled by the microcontroller. So basically when you switch the unit off, the microcontroller knows it's been switched off, and then what it'll do, it goes through a routine and saves all the relevant information, so when you switch the radio back on, it comes back exactly where you left it. That was another bugbear, by the way. A lot of people were complaining about that. So you switch it off, it does a routine and saves. Now this has got a lot of saving, you know, memory on capability, so you can write in memories, and it will save just about any information you want it to, and that's via this little IC here. This is a FRAM IC. This is one I played around with before, which is connected up again via I2C, and these are just links you can change the I2C address should it clash with anything. But that's 256 kilobytes. So yeah, FRAM's really good, doesn't need backup batteries, you can just write to it. It's unlike you know, you've got EEPROM in here. I'm very, very skeptical about using EEPROM on microcontrollers. I don't like doing it because they've got limited write cycles. And you know, if there's something wrong in the program, it'll just keep writing to it. And if you've got something like a 10,000 you know, time write cycle, you know, if it's the speed these controllers go, 48 megs, if something's wrong, it's just gonna crash it. And so you got to be very careful. So it's easy to use the FRAM. The FRAM has got a really high, I don't know exactly what it is, but you can just use that as RAM basically. It works very well, and it doesn't need a battery backup. It's fine. So the thing's configured. You switch it off, yes, switch it back on, and it's exactly where you left it. And there's another thing on here which you may have been looking at. This is the switch. Obviously, if you're doing development work, you can just, it's just a reset. It just resets the thing. So normally you wouldn't use it. I've used a very small one because this is designed to go in radio equipment. If there's wires everywhere, I don't want them touching the thing and resetting it. But yeah, that's about it. I mean, there's other things I was going to put on here. You know, you can control this via the USB. You'll be able to do it. I need to look at Ham Radio Deluxe or these controllers. It's very, very straightforward how all that works. It's a walk in the park. But that being said, it might be it still takes time to get it right. So, but I need to have a look at Ham Radio Deluxe or possibly speak to them, and we'll see if we can they put a section in for it, or I'll just copy you know, well-known sort of setup that they've got for another radio, and I'll just copy the same command so that it works. Okay, well, let's get this thing on the bench and we'll get it connected up and let's see what it is doing.